almost time. I think we're almost there.
So we,
Yeah, close enough. Welcome back. Yeah, question to start us out.
so you said we're going to be using the flow chart for the exam.
Yeah, it looks like we are so far decided that this will be our flow chart, or our notes to hand out for the third exam.
So it'd be out of the question to have both.
Sorry, say again?
It'd be out of the question to have both for the
Sadly,
exam.
yeah. It'll have to be one or the other, sadly.
Gotcha.
But never hurts to ask. And when we go to do the final exam, it's probably going to be 2 sheets. So it'll be something like this, and a back sheet without more problems, maybe some other interesting formulas. Other questions about the upcoming exam so far?
Will we still be able to use the AU 3x?
Yes, absolutely. So on your 3x5 note card, one thing I would recommend is the absolute convergence test. This is really a theorem that tells us when a series converges absolutely, it is convergent in and of itself. So that's one thing that is missing on that flow chart. And then anything else that you'd like to have on there, again, is you're welcome to decide on. For example, we won't have all the derivatives that we did have on the last exam on the handout. So you might decide on, if I could get there, when you make your note card, you may decide, where are the actual exams? You may decide to go to here, notes provided on exam 1, and just take out whatever information that looks like it could be useful. But you'll see that we're not calculating a whole lot of integrals and derivatives, so it would just be things that you saw in the homework or the lecture that look like or are noteworthy for the exam. Other questions about the upcoming exam then?
When is it going to be?
Well, that's a really good question. That's probably the question. Looks like next week is going to be a normal week for us, I believe. And it's going to be on the Thursday of the week afterwards. So let's see. It looks like April 11th, I believe. Other questions at the moment?
So next week we'll have 11.8.9 and 10
Mhm.
due before Thursday.
11.10 we may cover on the Monday of that week, or at least complete it by then.
Oh, okay.
So yeah, we're actually pretty far ahead. We're going to mainly hit these sections next week. Well, 11.7 is the review section, so mainly these sections next week, and 11.10 will be on the Thursday or Monday, excuse me, of the day we actually have the third exam. So we're actually running out of material quite fast. It's kind of exciting. Other questions about it?
The all the
Yeah.
problems that are on the series test flowchart,
Yes.
will there be a key for those at some point?
I do not have the key to those, sadly, but I have 2 sets of problems that have no keys on them. They're the summary of the test for series. So if you go to, no, it's not that one. The 11.2 to 11.6 review problems, I should hit the lights here. If you go to that document, then we have a set of series with no solutions whatsoever. I'm not sure what the source is to this. I'll have to dig that out. So I could either work on some solutions to these or work on the solutions to the back of this handout here, where there is something like, what is it, close to 40 problems. What would you folks feel like is more helpful?
Sorry, what was the question?
I could work on solutions to one of the sheets or the other. Probably I wouldn't be able to get all of the problems completed before the exam. So if I was to start working on a set of solutions, would this document or this document seem to be the more useful?
And I feel like the one with more problems on it.
The more problems, more homework? Okay, let's go for this one.
Do you have a preference?
I really don't, because I haven't actually looked too carefully at these, to be completely honest. I mean, they're all great. This set has 38 problems, which is going to use everything. And it's also going to use the absolute convergence test at some point as well. It's just not on that flow chart. I would have to double check that that's actually the case. This definitely is going to use the missing test on the flow chart. Something like, let's see if we can find it. This right here would require the absolute convergence test, because this is not an alternating series and it has negative terms. And if we look at this list, that looks like it has, is that the same problem? No, n cubed plus 4 and under a root. So it's got some of the same kind of things. So I can start working on this sheet here. Probably what I'll do is work on it in waves, where I just say problem 1, use so-and-so test. And then as time permits, I'll write out some of the details on another wave. And they'll be slowly uploaded as we get closer and closer to the third exam. Probably over this weekend, in the middle of this week, I'm going to post the sample exam problems as well. Other questions so far? Okay, so far the exam is going to cover sections 11.3 to 11.7, which will finish at the end of today. Then 11.8 to 11.9, 11.10, that's where we actually take all the work we've been doing and put it to good use. The reasons we're looking for whether certain series converge or diverge is for the following reason. If we look at the series, say, summation as n goes from 0 to infinity of, let's make this be alternating, -1 to the power of n plus 1. And then let's also throw in x to the power of, let's go for 2n plus 1 divided by a 2n plus 1 factorial. So this is just a random series. It's different from the ones we've seen before in sections 11.1 through 11.6 because there's a variable x in there. So the convergence divergence not only depends on n, it also depends on x itself. And the questions are, for what x does the series converge? So that's one important question we would love to answer. And in fact, we already have a test that can answer that. The ratio test would answer it. Another important question that we'd like to answer is, what does this converge to? So this is kind of interesting. In the case of a power series, we'll call this a power series just because there's a variable x to a power, and that's the only reason. We can also say exactly what function it converges to outright in certain situations. So we're going to eventually, down the line, answer the question and say that this function is really, truly a sine x. So we'll be able to finally give a definition to the trigonometric functions, sine, cosine, exponential functions, and so on. And that enables us to do more differential equations, find more antiderivatives, and that's really the whole purpose of 11.1 through 11.7, in order to address questions like these two for that kind of series. Any questions about that so far? Okay, so that's where we're going. First, we need to discuss some of our last tests before we get there. The last test that we did discuss was the ratio test, which has 3 conditions. We love the ratio test, first of all, because what it's great for is any series. So no matter what form your series takes, you can throw into the ratio test and get a condition of 1 for absolute convergence if the limit comes out to be something less than 1. We're putting in an L here to just remind ourselves it has to be a finite real number. Or if it's greater than 1 in the limit or diverges to infinity, the series would then diverge. So it's pretty great. You either have absolute convergence, which implies original convergence, or divergence. The downside to this test, however, is it can fail. And that's the third and very important condition. It's always good to know when a test fails, like the test for divergence, for example. It says if the limit, as n goes to infinity, of an plus 1 divided by a sub n is equal to exactly 1. Notice that's the one value that we've avoided in condition or possibility 1 and 2. If it's exactly 1, then the test fails, which is unfortunate. So although we can use this nice test, the ratio test, on any series whatsoever, there'll be plenty of them from which no conclusion can be drawn. If we get a limit 1, the test fails, and so we cannot determine if it's convergent or divergent. But nonetheless, it's still a very, very powerful test. So let's practice using it on a couple problems, and then we'll look at the very next one, the root test, which is the last test of the entire course. Any questions then before we give the ratio test some more practice? Okay, so let's go to another problem. Here this problem just says simply, determine the convergence divergence of the series. And let's start today with a nice one. Let's let it be the summation as n goes from 1 to infinity of -1 to the power of n minus 1 multiplying n squared plus 1 divide by 2 to the power of n. So that's our series. And potentially lots and lots of different types of tests could work on this. But what we like about this particular series is that it is alternating. And if we were to use the ratio test, the alternating portion or feature is going to disappear immediately because we take absolute values right off the get-go. We could possibly use another test. For example, it looks like it would alternate, so an alternating series test might be appropriate. But let's give this a try since it's our fancy new test. In order to work that test, we have to know what is the n plus 1th term, or the term after a sub n. So I would start off organizing this by writing what a sub n plus 1 actually equals. If we do that, then we'll have this as our a sub n, and we'll be able to form the limit. Let's call this summation as n goes from 1 to infinity of a sub n, just so we have a name for the thing. Okay, next, a sub n plus 1 just puts an n plus 1 every single location the index n has occurred. So a sub n plus 1 would be negative 1 to the power of n plus 1 minus 1, so just power n. Then we'll have here an n plus 1 squared plus 1, and in the denominator we'll have 2 to the power of n plus 1. So altogether that's our an plus 1, and that helps us to see what the limit should look like. Any questions to that step of writing out a sub n plus 1? Okay, then we're now going to use the ratio test, so we'll take a look at the limit as n goes to infinity of the absolute value of an plus 1 divided by a sub n. So whatever this comes out as, possibly the test fails and we have to use something else, but we might get a condition or conclusion of convergence or divergence. So first, we'll throw this into one overall limit as n goes to infinity. The effect of the absolute values are that it's going to knock off the negative 1 to the power of n. So if you didn't write that in on the very next step, that would be okay because we know it's going to vanish. But I'll write it all in this one time and just mention that's an appropriate shortcut. So this will be, first I'm writing a sub n plus 1. We take negative 1 to the power of just n, because we add n plus 1 to it, multiplying n plus 1 squared, plus 1. And for something like this, I probably just would leave it alone, because we have specific shortcuts to handle the limits of rational functions. But for this one, 2 to the n plus 1, I'd probably factor it as 2 times 2 to the n. Since once we deal with dividing by a sub n, there are cancellations we're expecting, and cancellations with the exponential function would happen each time in this case. So now we divide everything by a sub n, and instead of writing a huge division bar with another fraction, let's just immediately multiply by the reciprocal. And this is our a sub n. So if we take the reciprocal of this, well, the position of this we can think of as being in the numerator. So it'll be 2 to the n divided by negative 1 to the power of n minus 1, multiplying n squared plus 1. So all of that in absolute values. So it's a really gnarly looking limit at first because of the n plus 1. But once we do all of the cancellations, it really resolves very, very rapidly. So the next step on the limit would be that this is equal to the limit. As n goes to infinity, the negative 1 to the power n and power n minus 1 are all going to vanish due to the absolute values. And we also have 2 to the n and 2 to the n canceling as well. So all that's surviving is an n plus 1 squared plus 1 from the numerator. Down below, all we have left is 2 n squared plus 1. So that's the result of all the cancellations, the absolute value affecting all the terms. Any questions to that step so far with the limit? Now at this stage, which is a pretty common feature whenever you're using the ratio test, we should be able to just eyeball that and say exactly what the limit is through a shortcut. Anyone see what the limit is immediately just by inspection alone? Exactly, because the degree here would be squared above, and there's a 1n squared if we multiplied everything up. Here we have 2n squared plus 1, so we take the 1 from the numerator, the 2 from the denominator, and that would be the horizontal asymptote of that rational function, which means that's the value of the limit. So it's 1/2. Does that mean convergence or divergence for this series? Yeah, we have convergence. The limit came out as 1/2, it's less than 1, so this implies the series converges by the ratio test. Really, the conclusion on the ratio test is even stronger. We know that it doesn't just converge, but the convergence is absolute. So this is an absolutely convergent series, but if the instruction just said test for convergence or divergence, that would be okay to leave it like that. I'll assume that you said the following logic, that you know that this converges absolutely, but by this test, if something converges absolutely, this one, that implies original convergence of the original series itself. So you're okay to just take that as a shorthand. Or if you said absolutely convergent and nothing else, I assume that you know that absolute convergence implies normal convergence. But any questions so far with that ratio test? Okay, so really the major work of the ratio test is just organizational. We have to know exactly what the form an and an plus 1 takes, how to put it together, and carefully cancel through the limit. So let's do another extreme version of like that, where the organization is really the whole problem. Any questions at all first, before we change gears? Okay, so let me slowly build up an entirely new series, and let me hide the Java update. There we go. This one looks pretty horrendous, and it is one that's in the homework. The homework one is different, but similar in spirit, so we ought to do something like that. So the same instructions determine convergence, divergence. This is our series. It's not written with the summation symbol, so we have some work to get it to this point, but a series is always adding together infinitely many terms, and this is the form the infinitely many terms take this time. We'll start with 2/3, then we'll add to it 2 times 5 divided by 3 times 5. So it's as if we took 2/3 multiplied by 5/5. I mean, that cancels, but we're leaving it just as it is, just to establish a pattern of what's happening next down the line. There'll be plus. On the next one, we have 2 times 5 times 8. Then down below, it's 3 times 5 times 7. So what we did on the third term is we took the second term. Up above, we multiplied by 8. Down below, we multiplied by 7. And the spacing of the next factor we multiply is by 3 in the numerator, 2 in the denominator. So that can help us out down the line. Then the next term is plus 2 times 5 times 8 times something, 3 times 5 times 7 times something, and if we went 3 to the right for that factor 8, then from the factor 8 to the next, we should have an 11. And we're only going 2 to the right from the next factor down below, so the next one from this should be a 9. Then it goes plus, with a bunch of dots to say, and so on, and that's a thing to test for convergence or divergence. It really looks like a huge mess, but things like this actually come up quite a lot. And the context that this comes up are things along these lines. If you want to expand x plus 1 cubed, that is no problem, it's just tedious. And you can use tricks like the Pascal's triangle. But if you have x plus 1 to the power of 1/3, and you really want to expand that, if that is really your goal, to multiply out x plus 1 to the power 1/3 or power 1/2, then you're going to have to use the binomial series. And things like this are the kinds of things that are going to pop out. It's awful, but it's a practical problem because we do occasionally like to expand this without breaking anything in algebra. And this is the trade-off. We get some weird things. So now, next thing to do is, if I want to test this for convergence or divergence, it'd be really nice to have this, a formula for a sub n. So that's where the problem should start. We need to say that this is all going to be equal to this long line of summations. The summation as n goes from 1 to infinity of a sub n, where a sub n is equal to something. So once we say what a sub n is, we'll be able to immediately say what a sub n plus 1 is. Then the ratio test will work. We could just look at the limit of the ratios of the n plus 1 term and the nth term. So this is where I would start to pick up with the problem. But any questions to that step? So I haven't really done much. This would be the statement of the problem, and this is where the solution would start. I'm going to call it equal to a particular series, and we have to find a formula for its nth term. So we can say here, the formula for this nth term, well first, this is the first, second, third, fourth term. Let's pick up with the fourth term and see if we can find a pattern. It'll go 2 times 5 times 8 times 11 times, then I'll say dot, 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 all the way to a final factor. So really the formula is about the last factor we see on each term. If we can nail that and show that all these terms are coming out right, then we'll be in great shape. So down below it was 3 times 5 times 7 times 9 times, then dot, 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 a formula for the final factor down below. So that's the name of the game. Once we have the formula for the final factor, we'll have a formula for the entire nth term. It just looks really, really awful, but we're getting through it. First, let's try to take on what this should be as a formula. And let's see what it should be. There's a bit of a trick to these kinds of things, where if the first factor is 2, I might start with, say, a 2n, like that. So now if n is 1 itself, then that would mean we're really just going to the very first factor, n gets put in as a 1, and we get the 2. But if n is 2 itself, I need to come up with something like 5, eventually 8 to 11. That means we have to add some quantity. Anyone see what the quantity should be that we add to this? 3. Yeah, exactly. These terms, or these factors, are increasing by 3 each and every time. So that should be the plus 3 here. I mean, we still have to test this out to see if it actually works, but this is a start. Any questions so far? So likewise, down below, we can say that we have a 3n. Oh, let's maybe do this a little bit different. There is a problem with a 2n plus 3. Anyone see what the problem is? If we start at n is 1, we would get a 5, right? That's kind of problematic. However, this is something you can always do. Let's just treat ourselves to starting at 0. If we start at 0, then that would mean we put in a 0 there, and we pick up the 3. If we put a 0 here, oh no, that would not work. Oh, darn it. Let's try something else. So when n is 0, let's go with maybe, how about a 3 here and a 2 there? How do folks feel about that new arrangement?
Would it work for 2?
So if we put in 0, we would get a 2 as the first factor. If we put in, say, a 1, I should have a 2 times the final factor, which would be a 5. So it looks like it's actually working. At 3, I put in 3 here, so 3 by 3 is 6, plus 2 is 8. Yeah, I think that's all right. So the thing that we're incrementing by should be plus 2. The thing that comes as a factor, or excuse me, a coefficient to the n. So that should be a 2n plus 3, like that. Does that make sense so far?
So the displacement that we see as a series should be the coefficient in front of the variable, most times.
Yes, in this case, for this kind of setup. And getting it backwards is a problem. But remember, coming up with the nth term always is kind of a guess and check sort of deal. So it's okay to kind of experiment. Don't feel like you have to get the exact answer on your very first try. But what you should do is, after experimenting, let's run it through the paces. Let's see if I can get a1, which is 2/3, a2, which is 2/5 divided by 3/5, and maybe a sub 3. If I can get those many terms from my formula for a sub n, then I would be satisfied or at least on the right track. So let's start with 1. At a sub 1, what happens is we have just one factor, and we use just the far right-hand side by this formula. We'd be putting in, oh, we're starting at 0, aren't we? That's always really, really hard for me to remember. I'll highlight it so that I eventually remember. So if we start at 0, there's only going to be the one factor. We're plugging in 0 there, and we just get a 2. Plugging in 0 there, and we get a 2/3. So a sub 0 works out, but let's check a sub 1. We have to exactly get this. At a sub 1, we need 2 factors. The first factor should be from here, the 2, from there, the 3. The final factor is always this bit right here, which we had to come up with. So if we plug in 1, we'll have 3 plus 2 for a 5. If we plug in 1 here, we'll have 2 plus 3 for a 5 as well. So A1 is 2/5 times divide by 3/5. At this stage, it looks like it's possibly working out. Any questions to that step? Should we try one more just to be really, really sure? Okay, let's go for a higher rigor of evidence and do a sub 2. At a sub 2, we're expecting 3 factors. So we pull in these 2 factors here and the formula for the final factors. So we'll have 2 by 5 above, 3 by 5 below, and they'll be multiplied by, we're throwing in 2 here, so that'll be 6 plus 2, so 8. 2 here will be 4 plus 3, so 7. So 258 divided by 357, all multiplied. And at that stage, I would say, yeah, we probably have the right formula. This was a bit of a cop-out, but if that works for you, you're welcome to do that. You can start this at any index you'd like. That's just kind of weird. Or you could keep it in as 1 and just resolve what it should be here as a new formula, which is completely acceptable as well. Okay, so we have a sub n. That took a lot of work in and of itself. But remember, we're trying to test this series where a sub n is all of that for convergence divergence, which means, well, the only test that's great in a situation like this, where we have something that looks like a factorial, but it's not, is the ratio test. Remember that n factorial, or 5 factorial, is really 5 by 4 by 3 by 2 by 1. So we have something that's worse than a factorial. The numerator is extending by 3 and multiplying, whereas the denominator is extending by 2 and multiplying. That's really something very similar in spirit. Any questions before we go to a sub n plus 1? Okay, so once you have a sub n through this formula, a sub n plus 1 will look like this. It's going to have 1 extra factor than a sub n, and it follows this same pattern where we take the previous thing, just write it all out, so it goes 2 by 5 by 8, then I'll just put the dot 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 after the 8, 3n plus 2. Then down below it's 3 by 5 by 7, then dot dot dot, multiplying 2n plus 3, and we need 1 new factor. We do that by taking this formula and replace n with n plus 1. So we'll have here 3 n plus 1 plus 2 above, and below in brackets 2 times n plus 1 plus 3. Then the bracket closes, and that's our an plus 1. Now we're ready to go to the limit. Any questions first before we take a look at the limit? That looks like this. Okay, so now that we take a look at the limit, finally, by the ratio test, as n goes to infinity, of the absolute value, an plus 1 must always be in the numerator, divided by a sub n. So this limit will be equal to another limit as n goes to infinity. Notice that an and an plus 1 do not involve negative terms at all. So if you drop the absolute value bars in the very next step, that'd be completely fine. But sometimes they really matter, so it could be a best practice, unless you're really careful. So first I'm going to put in an plus 1 like before. This is just a lot of copying. 2 times 5 times 8 times 3n plus 2 times, this factors and expands to give us 3n plus 5. So that's the full numerator. Then down below it's 3 times 5 times 7, all the way to 2n plus 3. Multiplying, this one will expand to give us 2n plus 5. So that's an plus 1. Then we divide by a sub n, and this is, again, a tremendous amount of writing, so we'll just immediately multiply by the reciprocal here of a sub n. So if we write all that out, then the numerator is going to be 2 times 5 times 8, all the way to 3n plus 2. And the denominator is going to be, oh, I forgot to flip it. Let me try again. So that's a sub n, but we're dividing by a sub n, which means I'm multiplying by the reciprocal. So 357 goes in the numerator. 3 times 5 times 7, all the way to 3n plus 2. Oh, 357, all the way to 2n plus 3. Then the numerator goes to the denominator, so 258 all the way to 3n plus 2. So this, all in absolute values, is the limit that we have to take. It's probably the most terrible looking limit we've seen all class. But is it really that bad?
Would there be cancellation?
Yeah, that we can cancel, say, the 258 all the way to 3n plus 2 cancels this way. So really it's just a whole bunch of fluff, and really the major skill to get through all of this is to get everything down pat, so that when we take the limit, we have the precise value. Then likewise, 357 up to 2n plus 3, all of those will cancel entirely. There's really not much left then. We're now looking at the limit. As n goes to infinity, we can drop absolute value bars and write this as 3n plus 5 divided by 2n plus 5. So as it stands, is this a convergent or divergent series from what we see?
Divergent.
Correct. The limit's coming out as 3/2, which is bigger than 1, equal to 1.5, so it diverges by the ratio test. Then it's finally done. It's kind of a nasty one, but really just a problem of trying to get down the formula for the nth term, which is an unusual kind of situation where the new things are factors for the formula, then just writing down everything and getting through the limit. Any questions at all with that kind of problem? Yeah.
Couldn't we simply redefine the ratio test definition as the function for the final term of the a sub n plus 1?
What do you mean by the function for the final term?
So
Sorry.
in the example right here, just
Yeah.
taking 3n plus 2 over the 2n plus 3.
This one right here?
Yes.
Sorry, I got lost. Are you saying to do the ratio test on this right here? Or,
So the ratio test, we have the full.
yeah, the
explanation set.
full thing right here.
Yes.
Mhm.
And on all the examples we've had so far, almost the entire function is canceled.
Exactly, yeah. So it's, I think I see what you're saying. It's as if we really just did the ratio test on, well, not quite this stuff, but it was almost this kind of stuff that survived. 2n plus 5 versus 2n plus 3. But sadly, the an, if we look at an plus 1 divided by a sub n, there's usually loads of stuff canceling. But are you saying, is it possible to skip from here down to the conclusion down below?
Yes.
I think that kind of depends. If you took the limit of just this, for example, limit as n goes to infinity of a sub n, just this original thing, and we didn't look at the ratio, an plus 1 divided by a sub n, this will come out as infinity. So this means we would be using the test for divergence to show that. However, taking this as a limit could be pretty gnarly because of all the ways the factors are changing. It's not just taking the limit of this itself. So this limit is not 3/2. It must be infinity. And to show that's infinity, it does take quite a lot of work, sadly. So I think the 3/2 that we got here versus the 3/2 we got there are sadly kind of a coincidence in this problem. Other questions or comments about it? Did that answer your question?
More or less.
Okay. Other questions or comments then about that? Okay, so that's the exciting world of the ratio test. Again, it's a really powerful test unless the test fails. We haven't seen too many or any situations like that, but that's going to be kind of a feature once we go to 11.8. When we look at power series in 11.8, 11.9, and 11.10, where we have a variable x in the mix, and we use the ratio test, the test will almost always fail at some point, and we have to do further tests. So we're coming up to that neat situation in part 3. But let's go off to the root test next, just so we see how that one goes. Any questions first before we take a look at that? Okay, so the root test, on first glance, it really looks pretty terrible. If you have the ratio test down pat, then memorize all the conditions and the conclusions, well, there's no conditions, the conclusions of the test, then the ratio test should feel like it's almost the exact same thing. When we look at the root test, part 1, 2, and 3, this portion, and this portion are completely identical. So the conclusions you make are the same as what we've been doing with the ratio test so far. The thing that's new is when we take the root test, we're taking the nth root of the absolute value. So that's the only thing that changes. this portion right here, it's really hard to highlight a PDF, but I think I got it. So that portion right there is the only difference in the new test. So let's give it a try. The way these tests are proved are by constructing a particular geometric series, and that's why we have problems at the equals 1. You'll notice that the geometric series says we converge when something is less than 1, we diverge when something is bigger than 1 or equal to 1, and there's a failure at the exact equal to 1 in this situation when we use the geometric series. So next, let's take a look at a whole new series, maybe one where we don't have to come up with a formula for the nth term, because that is quite a lot of work. But instead, let's test this thing for convergence divergence. It is the summation as n goes from 1 to infinity of -2 times n divided by n plus 1, and for no apparent reason, the whole thing has been raised to the power of 5n. Okay, so if we want to take and test this for convergence or divergence, one thing to note is that if we actually use the ratio test, an plus 1 is going to be equal to -2 times n plus 1 divided by n plus 1, so n plus 2 really, to the power of 5 times n plus 1. So if we took a look at this, even if we hit it with, say, the absolute values to get rid of the 2 there, or even if we take, or excuse me, just absolute values like that, that's the test we want to use, then this is something really, really complicated to work with. If we divide by a sub n, there is cancellations, but there is still a lot of stuff that survives. So it becomes a bit of a chore to work with, the actual root test in every situation. So here we're going to, the ratio test. The ratio test really shouldn't be tried or forced to be used in every single situation. And the one thing that keys off that the root test is a good call is this n right here. So the root test is effective. The reason for that is this n right here is a problem if we were trying to do a test where there's n inside the base and n in the exponent at the same time. But the root test starts with taking the nth root, and it's going to immediately get rid of our biggest problem with this series. It'll delete that n, essentially. So let's work that out. Any questions before we give it a try? Okay, so in the root test, we take a new limit as n goes to infinity, and this time it's the nth root of the absolute value of a sub n. So in a situation where the root test is effective like this one, it's a little bit faster because I don't have to look at the ratio of an plus 1 over a sub n. We could just start immediately writing things out inside the limit. So now this is the limit as n goes to infinity. First, the absolute values are going to have the effect of deleting the negative sign. So I'll write this as the nth root of 2 times n divided by n plus 1 to the power of 5n. Okay, so I neglected to write the absolute value bars because we've destroyed the negative sign, and all that's left are things that are positive. Does that look all right to that step so far? Okay, so the logic of this test so far is that we're really just using an exponent law that says, say, x to the power of 5n raised to the power of 1 over n is just x to the power of 5, since the exponents must multiply in that arrangement. But if we're taking the nth root of anything, let's just call it a, that's really just a to the power of 1 over n. So we're really looking at an exponent of 1 over n, which multiplies 5 to the n, which tells us the new exponent is just 5 itself. So this is going to turn into the limit as n goes to infinity of 2 to the n divided by n plus 1 raised to the power of 5n raised to the power of 1 over n, and we have a cancellation going that way. Does that make sense, visualizing it that way? Okay, so after we cancel this n with 1 over n through exponent laws, it now turns into the limit as n goes to infinity of 2n divided by n plus 1 to the power 5. And at this stage, we can, once again, eyeball the limit. Anyone see what the limit has to be at this stage?
2.
Close. The power 5 is still on it, so it would be 2 to the power 5 altogether. The limit of the thing inside is still the limit of a rational function, so we could visualize doing the limit in this way. It could be written as limit as n goes to infinity of 2 to the n plus 1 to the power 5. And the reason that step works is the function that takes whatever you have and raises it to the power 5 is a continuous function, so the limit commutes inside that continuous function. The limit of everything in here is 2 divided by 1, so we have just 2 to the power 5, or 32. Then what would our conclusion be after taking that particular limit?
Inversion.
Yeah, so if we go over here, we have this situation. I mean, this is the wrong theorem, right? But the only thing we changed was the type of limit. The conclusions are exactly the same. So if we get a limit that's larger than 1, the test works, and it tells us divergent, like you said. So I'll write here greater than 1, just to emphasize. I'll write that it diverges. And we already indicated the test we want to use twice, so we could just end it at that step. So that's how the root test goes. It's really a very, very fast test when it works. I just wouldn't use it on a lot of stuff. I would be looking for this every time before I decided I wanted to use the root test. But any questions about it so far? I guess I have a question then. Should we try another one? Okay, let's do another root test. So this one goes, let's pick out a good one. How about n goes from 1 to infinity of a sub n is defined to be as n goes from 1 to infinity of 2 to the power of n plus 3 divided by n plus 1 to the power n. So that's our thing to work with. This is a different series from the usual because the terms are positive. So taking the absolute value and then the nth root is a little bit overkill. We're just going to effectively be taking the nth root on this one. But the trouble also is that powers are a bit off. So if we do a little bit of preliminary algebra on this, we can simplify it before we get to the limit. So let's take a sub n, which is all of that. And what we would like to do is get this kind of situation where things are ready to cancel, and we don't have to do a whole bunch of algebra to get there. So what I would like to have is the exponents to match, so I can make the base be one thing to the common exponent. So 2 to the power of n plus 3, to get there, can be written as 2 cubed times 2 to the power n, then no change in the denominator. So if we take that step, then we can use exponent laws to essentially factor out the exponent, n, place it on the outside, and it's affecting the new base of 2 divided by n plus 1. Now that makes it just a little bit easier to work with. But any questions to that step? Okay, then we're going to use the root test once again, only because of this right here. We have an overall exponent n with a base that also depends on n, which always means the root test is highly, highly effective. And we take a limit as n goes to infinity of the nth root of the absolute value of a sub n. So let's write out what that is in this problem. Once again, we don't need absolute values. All the terms are positive. The nth root is just an exponent 1 over n, which would multiply this right here. So you could just go right to the end answer in one step, but let's take a little bit to get there. We have 8, 2 divided by n plus 1, risen to the power of n. The nth root comes in as a power 1 over n. So we want to take that limit. Any questions to that step so far? Okay, so this power 1 over n has to distribute to everything inside. So first it distributes to the factor 8. And we get limit as n goes to infinity 8 to the power of 1 over n. Then it distributes here, but that's a cancellation. All we get is a 2, so times, that's an n, it's a horrible n. We get a times 2 in the numerator, and an n plus 1 in the denominator. So after the cancellation with the exponent, and also distributing it to the base 8, this is what we're looking at. Then the 2 can move out if you really wanted to. This could be twice the limit as n goes to infinity of 8 to the power of 1 over n divided by n plus 1. However, we didn't move the 2 out because we can. We didn't necessarily have to. But what is the reason we cannot move out the 8, whereas the 2 could move? Yeah, the 8 is frozen inside the limit only because of the n is affecting it. The 2 can be factored outside the limit because it did not depend on n in any way. So now we take this limit. What we can say now is, if we look at what's happening in the numerator, we're taking larger and larger roots of 8. So this is going to converge to some constant, it looks like a 1. Does that make sense with that one? Okay, we could do the same kind of trick we did over here, provided the bottom converges. The limit can go all the way up to the 1 over n, so in the limit that would be a 0, and 8 to the power of 0 is exactly 1. So the numerator is getting smaller and smaller. The denominator is getting larger and larger. So what is the value of the n limit?
0.
Yeah, the numerator shrinks, while as the denominator gets larger without bound, we get a 0 in the limit. Okay, so that means if we got 0 in the limit, we're on this condition right here. We have absolute convergence, which implies usual convergence in this situation. Any questions with that so far to that step? Okay, so now we can say that the series converges. Again, if you left it there, that's okay as per the instructions, which we're asking if things converge or diverges. Or you could say it converges absolutely, which is a stronger conclusion that the ratio test and the root test both give. But absolute convergence does imply convergence, so really either way answers the question. So that's the ratio test, the root test. They're pretty powerful tests, but the root test is only used in certain niche situations, like the ones we've been looking at. Any questions then with all of the tests now on the table? So we've done it, folks, from section 11.1 all the way to 11.6. This is every test for the convergence and divergence of sequences and series. Next thing we'd like to do with the remaining time we have is just look at practicing all of the tests together at once in section 11.7. 11.7 itself is meant to be a review section, and that's why I don't actually have any 11.7 notes. There's not much to say. We're just doing review problems. And it's also why the homework is really kind of short. If you want more practice problems, there is plenty more in page 746. But let's do a set of problems like these just to get familiar with using the tests. Any questions then before we start? Okay, let me pull out the flow chart since it looks like this is what we're going to be using for notes on the exam. It'd be a good idea to familiarize ourselves with it. I would probably recommend just printing that as soon as possible so that when you're solving things on the homework, you have that readily available and you don't have to familiarize yourself with the entire flow chart while you're doing an exam. So this is now 11.7. Let's just call this a review section because that's what it is. And the instructions for every problem here are to test for convergence, divergence. And let's go to just a random sequence of problems. First one we're going to do is summation as n goes from 1 to infinity of -1 to the power n multiplied by n times n squared plus 2. Okay, so that's our series to consider. If I was taking this as an exam problem, I would probably take a few moments, maybe 20 seconds, 30 seconds, a full minute, before I write down anything at all, just to decide whether I personally believe it converges, diverges, and also to decide what kind of a series it actually is. So first, what kind of a series would you say this falls into, if anything?
Alternating series?
Yeah, we are alternating from -1 to +1, so the alternating series qualifies for this thing. Next, would you say it converges or diverges based on its form?
Diverges.
It may diverge, yeah. Anyone else? Converges possibly? Hard to say. We do know that if I looked at this, it'd almost be as if we're dealing with something along the lines of, say, summation 1 over n. I could compare it to that, which would be the harmonic series, which does diverge. However, it is alternating, but those are good thoughts to also keep in mind because the alternating series as a test has a bit of a problem. If you know that the sequence b sub n, the positive terms, is decreasing, and if you know that the limit is 0, then it converges. But there is no conclusion for diverges like we have for the p series, like we have for the geometric series, and so on. So if we believe it to be convergent, then we pick the right test. If we believe it diverges, however, the alternating series test really cannot be used at all because it only has a conclusion of convergence itself. So let's give it a try. We said it's alternating. We're going to hope the test works. If it doesn't, we'll go to the very next test. If this test fails, the very next test is always the test for divergence. If my alternating series test fails, that's the best place to go to immediately thereafter. So first I'll use the alternating series test. The steps you have to take for this test is you have to say what b sub n is. So b sub n, let's write it this way, let b sub n be equal to something. What would you say that b sub n is in this problem?
N over n squared plus 2.
Exactly, it's everything except the alternating part. So we grab n, divide by n squared plus 2, and we can go from there. So we have to do a couple things while we're at it. First, let me do the limit. The limit as n goes to infinity of b sub n, what would you say that limit should then be if we're looking at n divided by n squared plus 2?
0.
Yeah, these are some of the best limits ever, right? And they're so pervasive that you should really treat yourself to that shortcut. If you want to do that limit long form, you go to the denominator, pick the most important dominating term in the denominator, and divide every single term by n squared. And then you can see that this comes out to a 0 in the limit, since everything is going to be divided by a power of n. Okay, so the limit is 0, and as a sequence, b sub n is decreasing. Does that make sense why it should be decreasing as well? Okay, if we're not ever completely sure, if the function just looks crazy, maybe it has things like exponentials, logarithms, or trig functions inside of it, the first derivative test would be something to use. And that might be something that happens in the homework. You can always ask if it's appropriate to just say decreases, or if you need something more powerful. On an actual exam, this would be sufficient, because we're trying to focus on the material we're being examined on, which is the alternating series test. So if it's clear to you that it's decreasing, just assert it, and I would be just fine with that on an exam situation. So this is possibly more important, but they're both important. We can now conclude, or say this shows the series converges. As soon as we have these conditions fulfilled in yellow, again, it's not going to be printed in color. ISU cannot afford color printing apparently. But whatever these conditions in the boxes in the middle are fulfilled, that would mean you have a conclusion of convergence for this test. What questions so far about that? Okay, so that's one down. Really the whole strategy here is to pick the test that looks like it can work and decide what the situation should be, convergence or divergence. So let's try something else next. How about k equals 1 to infinity of 2 to the k multiplying k factorial divided by k plus 2 factorial. So that's our new series to test. It's a mess, but what looks like should fit for this one.
Ratio test.
Yeah, really, what's popping at us that definitely ratio test has got to be the way to go this time. Let me scroll to the ratio test.
Was it there?
What was something that's striking you as definitely ratio test whenever you look at that series? What's the thing that's popping at you?
Factorial?
Yeah, the factorial. If you see a factorial, then probably the ratio test is the way to go for this kind of thing. So let's run through that ratio test. Any questions first before we give it a try? I guess I have a question for folks. We have done the ratio test a few times. We could go to just a different one and decide what the test is. Or does it be beneficial just to go through the test? Okay, let's go through the test. Since we have only done it 3 times, that's not a whole lot. So to go through the ratio test, we need to analyze the limit as n goes to infinity of a sub n plus 1 divided by a sub n in absolute values. Usually when I do this, I carefully write out what a sub n plus 1 should be. And I forgot, it's k this time. That's a big conflict for me. A sub k plus 1, and the limit as k goes to infinity. I hate changing the variables for that reason. So let's deal with k this time. And this time, let's just dive right in. The limit as k goes to infinity of the absolute values of, we're taking this and putting in k plus 1. So 2 to the k plus 1 should be factored as 2 times 2 to the k, because we're expecting a fancy cancellation. Then this turns into k plus 1 factorial. But k plus 1 factorial is also equal to k plus 1 times k factorial. So that's the best way to insert a k plus 1 factorial if you're using this test. Does that make sense with that factorization there, with the factorial? Okay, kind of the idea of it is if you write down anything, say something along the lines of 4 factorial, this is 4 times 3 times 2 times 1. But this portion here is 3 factorial, so it could be written as 4 times 3 factorial if you'd like. And that's essentially what we've done up there with the k plus 1. We can take the leading portion, k plus 1, and multiply it by the factorial of 1 integer less. So let's throw that in here, k plus 1, k factorial. We don't need that big of a fraction bar. Then we'll do the same thing with that down below. Or should we? Well, I guess because we're going on this route, let's keep on going. What we could have done, which might have been better, it's always good to look before you leap, this whole thing could have simplified, so we could have taken that step. Simplify the series first to make this a little bit nicer. While we're doing the trade-off, we made this a little bit worse, and we didn't have to simplify that. So let's continue on so we don't have to erase. Does that sound all right to everybody? Okay, so now I need to handle k plus 2 factorial. What would you say the way to factor k plus 2 factorial should be? What would you get out of that one?
Would it be k plus 2 times k plus 1 times k factorial?
Yeah, exactly. If we had cause to go further, we could have, let's say, times k minus 1 factorial. In other words, this pattern continues off forever. So let's drop that down below. K plus 2, k plus 1, k factorial. And notice there's already a cancellation inside there. We have not involved a sub k yet. So that just means we could have possibly simplified this work. But let's continue on. It's too late to fix it without erasing, which is counterproductive. So this goes all the way off to, now we throw in a sub k, which is all of this, but we're dividing by a sub k, so we just have to remember, do the reciprocal. So first it's k plus 2, and that is the same as k plus 2, k plus 1, k factorial, and that's the whole denominator. Then up above, oh, hang on, there's a problem with this. I think we have a problem right here. So k plus 2, k plus 1, k factorial. Sure, that's k plus 2 factorial. But this is a to the k plus 1, right? So we didn't do the plus 1 on that. Darn it. So almost everything got the plus 1 except this. K plus 1 plus 2 factorial is what should have gone in the denominator. We forgot our plus 1 on that. I guess there is some really good value in just writing out a to the k plus 1 first, just to make sure everything is in pat the first time without double checking. Does that make sense what the problem was with that first fraction? Okay, so we put in k plus 1 almost everywhere. Here, here, but not there. K plus 1 plus 2 factorial is really k plus 3 factorial. But now we know the specific way this should go. It should be k plus 3, k plus 2, k plus 1, and then finally k factorial altogether. Then this fraction that we're building here comes from a sub k. So it's the reciprocal of this. We use the formula for k plus 2 factorial to get that numerator. And 2 to the k times k factorial is the denominator. Okay, so that's everything in all at once. Really should have simplified it first. If you ever notice factorials over factorials, that's probably the best thing to do. Simplify first would have been a better option. But we've got it all there, and now we can treat ourselves to some cancellations. Any questions first? Does that look all right to folks? Okay, let's get canceling then. We can kill off 2 to the power k. So that's gone. K factorial is gone. And there's lots and lots of k factorials, so it's gone in several places. Then k plus 2 times k plus 1, those would cancel as well. It looks like all that we have left is k plus 1, k plus 3, and a 2 in the numerator, provided everything was canceled. Does that look okay to folks? Okay, so finally we can say that this is equal to the limit as k goes off to infinity of absolute value bars were redundant all along because everything is positive. So we'll drop absolute value bars. In the numerator, all that's left is 2 times k plus 1. And the denominator just has the sole survivor, k plus 3. So the limit of this whole thing would be 2. So we've done it. We're ready to state our conclusion. We used the ratio test. We had a value of 2, which is bigger than 1. So the conclusion is it diverges. Then that problem is over. Any questions with that one?
Could you just show the simplification of like the original?
Yeah, I really would have liked to have done that now that I saw how it goes just the brute force way. What we should have done is taken a look at a sub k to start. So a sub k is all of this stuff. Let me just copy it quickly. It's 2 to the power of k times k factorial divided by k plus 2 factorial. But that's the same as k plus 2 times k plus 1 times k factorial. So we have a cancellation going this way, leaving 2 to the power k, k plus 2, k plus 1 down below. So when we look at that, it means the original series itself is also equal to k goes from 1 to infinity, 2 to the power of k, and we have k plus 2, k plus 1. So this is just much, much easier to work with. And what helps with that new form after simplifying a sub k is now a sub k plus 1 is 2 times 2 to the power of k. Adding the plus 1 here will give us that. Down below would be k plus 1 plus 2, so k plus 3. And here will be k plus 1, so k plus 2. So if we went that route, then this and this would have been essentially the same. We have 2 to the k factorial. We would have had just this. So there would have been no k factorials on that portion. And over here, we should have just gotten 2 to the k plus 3, k plus 2. And everything else should have been gone. Cancellations are still the same. Oh, no, I made a mistake there to there. The cancellations are still the same, but it's just much, much nicer to get through if we took that one step to simplify. Other questions or comments with that one so far?
How many points would you take off an exam if we accidentally used the wrong variable?
if you say just n instead of k,
Yeah.
I don't think I would have taken off any points. I might have circled it and put in n itself, or excuse me, a k itself, the correct thing, but I don't think that would be worthy of taking points off for. What are the questions so far? Okay, so that really kind of gets us to the end of our time. My goal is to solve these ones down here. This is going to be a process. So once again, it's going to be in a set of waves where I'll just indicate what the test would be. Then maybe I'll go through them again and do some of the steps of the test on the particularly nasty ones and go from there. If ones look just really, really bad that we want to see solved, then I could try to focus on that one. Looks like there's some monsters in this list. Natural log to the power of natural log, for example. But really the whole goal with all this, as you try it yourself, is to just look at these and decide what should the test actually be. So say, for example, our last minute, let's take a look at something we haven't dealt with yet. How about, or at least not today, what would you say the test should be for number 3? 1 over n squared plus n.
Comparison test?
A comparison test would do the job on this. If we look at 1 over n squared plus n, this is very, very similar to a p-series. In a p-series, we have 1 over n to the power p, and the only thing that's throwing us off from this is that plus n is the situation there. So what we could do is, possibly the limit comparison test is the easiest one to use in this case. I would compare this to 1 over n squared, just using the dominant term, which is a convergent p-series, and show that this converges by limit comparison. Then there's all sorts of things that we could also test the same way. This one could possibly be, because if the signs are worked out just right, the limit comparison test or just the usual comparison test as well. But we'll go through these in a little bit more detail. Maybe one last one for the road. What would you folks say should be the way to do number 6?
The root test?
Yeah, what strikes us as definitely a root test is this right here. If you have an outer exponent, and at the same time n is playing the role as a base, then that's got to be the root test. There's no other great way to handle that. And the one you should compare that to is something like this, which is a geometric series test. The difference is n is only an exponent in 5, and n plays a different role in number 6. That's why the tests are so different, going from problem to problem. But I think we've ran out of time. If you have any questions, feel free to stick around. I'm happy to help.
Could you also do an alternating series for number 5? Or does it have to be a -1?
Alternating series test. The trouble with this one and the alternating series test, oh wait, no, this could converge. Yeah, I think you could use that on this one. Yeah, the alternating series test would work on this. That's interesting because it's a geometric series. The geometric series test might still be a little bit faster, but it's good to know that there are options on it. You know, maybe it's not, because the geometric series test is going to require us to rewrite all of these exponents to get the common ratio. So that could be a chore, actually. Possibly the alternating series test may be faster. Sometimes it's hard to tell.